Oh yeah, sorry, I'm late. But I was just waiting for Valerie and what? Professor Kim went to play LOL. Be back later's. Valerie. This is so typical. You're supposed to teach proportional control. She's out playing games. Well, never fear. I have a backup plan. So today we're going to talk about proportional control, and this is, if you remember our basic drawing from before, we have the reference point for reference here, and then we have our summation, positive, negative. Then we have a control here, and we're calling this G of C, and then we have our plant, right, G of P, and then our output, whatever it is. And then we feed that back through here, and the goal is to make control this output, Y, to be the same as this reference. And this is the basic feedback control. So what we're going to do, and we derived a transfer function for this system, we'll look at that later. First, we're going to derive an equation for a system, which I'll introduce in a second. And then we're going to derive a controller. So first, let's look at how to derive this system for our system and then our control. So say we have a poro. This is a cute little poro, and we need to feed him. He's hungry. So he's over here. He's maybe, I don't know, jumping around. But he stops in a certain location, and we want to feed him this poro snack, so a little snack. But he's not very smart, and he will only come and eat the food if it's directly in his line of vision. So he's standing here, he has a direct line of vision right here. Okay, this is his line of vision, and we, for some reason, are restricted to only pushing this poro snack around by pushing it up or down vertically in this dimension. So what we need to do then, we've made a system. This is our system here, and we have a control objective. Our control objective is to get the poro snack to this point so that the poro will come and eat it, right? So here is our setup, and we're going to model this, and then we are going to build a controller for it. So let's start the way we usually do. Here's our poro snack, and we are going to define, of course, some axes, because that's what we have to do. So we're going to call this position Y, and we're going to label this as a positive. And of course, this snack has a mass, so we're going to call it M. We are going to input a force into it, and for us, we're going to pretend that it can only move up and down. So we're going to put an input, and our U will be going in the same direction as the positive Y direction here. And of course, we're not going to ignore friction. There's a force of friction, and that will go back on, will resist the movement. So we'll also have a force of friction. Let's call it friction for now, equal to negative B, and this is a positive coefficient, and it will be with Y dot. And of course, we will use our equation, F equals MA, where our A is equal to Y double dot, right? Their derivative of the position. And so this was our setup. This is familiar, hopefully, from this system modeling we've done before. But the new aspect that we're adding in is that we have this reference point. So we're going to call this, I'm going to kind of add some room here. This is going to be called Y reference. And this is where we want to push the food, the location of the food, to in order to meet our control objective. Because once we are able to stabilize it there, our poro will see it and we'll be able to achieve our goal of feeding the poro. So that's our setup, and now we're going to go and actually talk about what kind of control we're going to use and how we're going to model it. So we just explained our system, and let's try to bring it back to our system diagram here. So our reference is now our Y ref, which is the ideal snack position ideal, I guess, snack position. And then y is our snack position. And we'll call this ideal or goal, something like that. So it's our reference point. We want it to go there. Our system is essentially our snack system, snack moving system. So snack moving system. Let's put that in our system. And our control is our input to it. So here is the error right between these two that is fed into it. So we'll just call this our control, because that's really what it is, and we can change what's in here. First, let's look at the system, because we just described it, right? So our snack moving system, so F equals ma. I'm going to do this quickly because I think everybody knows how to do it very well already. And our forces here were equal to u, the input, minus b y dot equals m y double dot. Take the Laplace transform of that. U minus b s y equals m s squared y. We want to get the output over the input, so we can move this over there. So we get m s squared plus bs. This is our y. And then we want output over input, so we'll move this over here and move that over there. And we will get y over u equals to 1 over this value. S squared plus bs. And I'm going to go ahead and get rid of this first coefficient here. So we're going to multiply by 1 over m on both sides. And our final transfer function for our plant will be equal to 1 over m here on the numerator, and then s squared plus b over ms. Here is our plant system. And if I ask you about this system itself, you'd see that we could take an s out of the denominator, meaning that we would have, this is equivalent, right, to our poles would be s times s plus b over m. So we would have a pole at 0 and at negative b over m. So actually that's not a stable system, right? Because they're not strictly in the left half plane. So next we'll actually look at our controller, because we're looking at a feedback system, not just the plant itself. So now we have our plant system, but we need to actually find the control system. So what we're going to introduce now is something called proportional control. So we'll bring it back to our other system view to explain proportional control. So we're going to talk about something, the most basic type of control in terms of feedback control, and we call it proportional control. So proportional control. And the basic idea is we know the position where we are. This is our current position. And so we'll just call this y. It's at this exact moment. And we know our y ref, where we want to be. So we pretty much take the difference of that. So we subtract. So we call it the error. And we take y ref minus y. So that's our error. So we have a certain amount. You know, we're not at our reference point yet. And so we have an error. And we can input, right? So we have an input, our u here, which is just going to, u, which is just going to be, you know, some force put on the snack. And the question is, how much force do we put onto it? Well, one thing that you can say is, well, if there's an error, you want to push it forward. So you could say, well, our input should be equal to some constant, which we'll call k, times the error. Right? So if the error is positive this way, we'll put a positive force onto it, move it towards the VREF. And then if, for example, we happen to be over the line, right, then our error here would be a negative value. So VREF minus, now we have a higher y, so this would be E less than 0, right? And then when we plug that back into here, a negative E times a positive, well, in this case we're going to assume K is positive, would be a negative U, which would just mean that we push it back in this direction. So this basic idea for control, called proportional control, works whether you're below or above the reference point. So this is the very basic, most basic type of feedback control, just called proportional control. You look at the error, you have some constant, you multiply the error by a constant, and that is the force that you apply to the system. So the idea is that that would help you move towards your y reference and achieve your control value. So now we're going to find the transfer function for the control, for proportional control. And we just mentioned that it's essentially the error, so E, multiplied by K, gives us our input. So this is, this would be our input into our plant system. All right, so relatively simple. If we take the Laplace transform of this, we just capitalizes our error is E becomes capital E. We have a coefficient of K, and that equals U. And for this system, our output is U, and our input is E. So what we want to get is U over E. So we can move this over here. So U over E is equal to just K. So in short, our transfer function for our control is just equal to K. It's very simple. So this is our transfer function for proportional control here. And then we have our transfer function for our system, our snack moving system, which I've rewritten here. Right? So now we want to look at the whole system transfer function. And with the feedback, if you remember, we have to look at a new system. So here, I'll write it. I'm going to move this over here just so we have it all on the side here. Equals K. Remember from our previous video, for a closed loop feedback system, our total system, we're just going to call it T of S, and the total transfer function for that is equal to GC times GP, 1 over 1 plus GC times GP. So let's take our two values here, our transfer function for the plant and the controller, plug them in here and see what we get. Okay, so we have 1 over m here. We can fit it in here. 1 over m on the top. Multiply that together, we'll just have a k out here. And then over this value, so we have s squared plus b over m s. So that's our numerator value here. And then we have 1 plus that same value. So 1 plus, so here again, k over 1m, s squared plus b over m s. It's a little bit ugly, but if we multiply both sides by the denominators that are in both of these, so s squared plus b over ms, squared plus b over ms, we should get a nicer form. Okay. And then here, now this is that 1 is multiplied by this, so we have s squared plus b over ms. We multiply it like this, this all cancels out, so we're just left with plus a k over m. So this would be our transfer function of our entire system. And here you'll notice that in the denominator, we don't have necessarily an a 0. So we actually can control the value of k. We can choose that because we're the designer. We can choose this value in here, and we can actually affect how the system will react to the dynamics of the system. This happens to be a second order system, so we could use some of our other analysis and try to change the natural frequency and see if we can get a certain damping coefficient. But from here, because we know that we can change our k values, we now have control over the system. So I'll stop here with just the transfer function, but from here we can do a lot with the system, and we can try to change different aspects of the system. So this is how we implement proportional control to a system, and this is how we can model the stability of the entire system, the transfer function, and then from there we can do further analysis and try to control the system to act the way that we want it to. Oh no, Poto found the whole bag of snacks.